Alright, so this is going to be an electric field strength example problem. Our goal is to find the electric field strength at point A. So point A is here at the origin, and we're finding the electric field strength due to charge 1 here of a negative 6 microcoulombs. And since it's a negative charge, the field lines are going to point towards that charge, so they're going to go through the origin into the first quadrant. So that means our electric field strength is going to have a positive x and positive y component to it. And then we have charge 2 here that is a positive 4 microcoulombs. So since it's positive, the field lines are going to point out of that charge. So it's going to point along the y-axis, or along the x-axis I should say, in the negative x direction. So remember, the rules for negative versus positive are different for forces compared to electric fields. Alright, so I want to find what that net electric field strength is at point A here. So that means I have to use vector addition to add the electric field of 1 and to the electric field of 2. And since they're vectors, we need to split those electric field strengths into components, use the component method to add them together, and then I can get a magnitude and direction for the electric field at point A. So the first thing I'm going to do is find the electric field strength for charge 1 and the electric field strength due to charge 2 at point A. And then I will split those into components and use the component method to add them together. So for the electric field, since we're dealing with point charges still at this point in time, I'm going to use the equation, the Coulomb constant times the charge, divided by the distance from the point of interest to the charge squared. So I plugged in my constant of 9 times 10 to the 9, times the 6 times 10 to the minus 6 coulombs. Remember, we're still using absolute values. And then the tricky part here is I have to figure out the distance from point A to the charge. And since I know this distance is 30 centimeters, and I know the angle in here is 30 degrees, I'm going to use the idea that cosine is equal to adjacent over hypotenuse, and I'm going to solve for the hypotenuse. So that gives me a distance of 0.346, which I can then plug in down here. So that gives me an electric field strength of 4.51 times 10 to the 5 newtons per coulomb. Now I can do this for charge 2. So I plugged in the Coulomb constant of 9 times 10 to the 9, and then I multiplied that by 4 times 10 to the minus 6 coulombs. And then the distance here, I converted that into meters, so 0.3 meters squared. And that gives me an electric field strength of 4 times 10 to the 5. Alright, so I have the two magnitudes. Now I need to break those into components. So for the one due to charge 1, so this one right here, I have my 30 degrees here. So I can do E1x and E1y. So since the x component is adjacent, I'm going to multiply by the cosine of 30, and since the y component is opposite, I'm going to multiply by the sine of 30. This one here, our second electric field strength, we really don't have to do much to convert that into components because it's entirely in the x direction. So negative x, I put the minus sign there, and then the y component is 0. So I'm going to add my x's together to get negative 9.42 times 10 to the 3 newtons per coulomb. Add my y's together, which gives me 2.26 times 10 to the 5 newtons per coulomb. Then in order to get my magnitude and direction here, I'm going to use Pythagorean's theorem. So the electric field is equal to the square root of the x component squared plus the y component squared. So that's going to give me 2.26 times 10 to the 5 newtons per coulomb. And it looks very similar to the y component because the x component is so small. And then in order to get the angle, so you can sort of see I've already drawn it in here, we have Ex is negative, Ey is positive. So this would be my hypotenuse, and we're looking for this angle in here. So I'm going to do the idea that theta is equal to the inverse tangent of Ey over Ex, and that is what gets me the 87.6 degrees above the negative x-axis. And I expect it to be very close to 90 simply because almost everything is acting in the y direction since the x component is so small. So the way I've actually drawn this is not to scale. It's just easier to draw it, making it look like a 45-degree angle. But really, it should be more up in here, closer to the 90-degree axis. Alright, so that is how you take the electric field strength from 2-point charges and add them together using vector addition to find the electric field strength or net electric field strength at a particular point.